In this example, we want to find the zeros of the polynomial function and then write the function in factored form. So remember, the zeros are going to be the x values that produce a y value of 0. And since this is a polynomial that doesn't factor by any of our traditional methods, we want to start by using the rational zeros theorem to first start by listing the possible rational zeros. The rational zeros theorem says that we are going to list all of the factors of the constant. So in this case, that would be all of the factors of 2, which would be both plus and minus 1 as well as plus or minus 2. And then you're going to divide all of those factors by all of the factors of the leading coefficient, which in this case is 5. So all the factors of 5 would be plus or minus 1 and plus or minus 5. So if we do that division, we are going to get a list of possible rational zeros. So 1 divided by 1, or plus or minus 1 divided by 1, gives us plus or minus 1. Then we have plus or minus 1 divided by 5, so that's plus or minus 1/5. Then we're done with the 1 in the numerator, and we'll go on to 2. 2 divided by 1 will be plus or minus 2. And then the plus or minus 2 divided by 5 will give us plus or minus 2/5. So rather than choosing a random value as our starting value to try to see if it's a 0, we're now going to choose a value off of this list. And of course, we always will start with 1, and if it doesn't work, then we'll move on to -1. We'll do the integers before we mess with the fractions. So let's go ahead and do our synthetic division with 1. Take a look at your polynomial and make sure that you are not missing any terms. In this case, we're not missing any terms, so our coefficients are 5, -17, -9, +11, and -2. So in synthetic division, you drop the 5 down, then you multiply the 5 by the number in the box, so 5 times 1 is 5, and then you add straight down. Then you multiply, in this case, -12 times the number in the box would be -12, and then you add straight down again. -21 times 1 in the box is -21, and you add straight down. And then -10 times 1 would be -10, and that would give us -12. Now this is our remainder. And using the remainder theorem, remember, that means that we do not have a 0. 1 is not a 0 because we're getting a remainder of -12, and we need to get a remainder of 0. So 1 doesn't work. So then we're going to move on to -1. At this point, I would recommend that you pause the video, do your synthetic division, and then check back with me. So hopefully you were able to get that -1 does work because we ended up with a remainder of 0. So that means we have our first 0. So when we list the zeros, we know our first 0 is going to be -1. Now, when we take a look at what is remaining from our synthetic division, this row here, the 5, -22, 13, and -2, those are the coefficients of our quotient. And since the original polynomial was degree 4, this quotient is going to be 1 degree less. So this is 5x cubed minus 22x squared plus 13x minus 2. And we're essentially setting this equal to 0 and trying to find the remaining 3 zeros. Now, if this equation were to factor by grouping, then factoring would be our most efficient method. But sadly, this one does not factor by grouping, so we have to go back to our list here of the possible rational zeros, and we're going to grab another value off this list and test it out. Now, if you were completing this problem entirely without your calculator, you would need to do your synthetic division again until you found another 0. But with our calculator, remember, we can use our calculator to basically do function notation. So for example, I can compute p of 2 on my calculator. Now on the calculator, it's going to look like y1 of 2. You might need to review those keystrokes. And when I substitute 2 into this polynomial, I get out -72, which tells me that 2 is not a 0. Then I would try -2 next. So again, p of -2 is what we would write on paper, but in the calculator, it's going to look like y1 of -2. So utilizing our calculator and substituting in -2 into the function, and you'll see that -2 is equal to 156. So sadly, -2 doesn't work either. So then we've got to move to the fractions. So we'll try 1/5. So p of 1/5, or in the calculator, y1 of 1/5. And remember, the keystrokes I've shown earlier in a calculator video, but if you needed help with this part, certainly come and see me and I can help you with the calculator keystrokes of how to do this effectively. But 1/5 doesn't work either. It looks like it gives us a negative 0.288. So then we'll try P of negative 1/5. So P of negative 1/5 is going to give us negative 4.416. And moving on the list, at this point in time, we're tired. We'll try P of 2/5. So P of 2/5 finally gives us 0. So we know one of our other zeros is going to be 2/5. So we're going to come over and do our synthetic division with 2/5. So here's 2/5. I'm just going to stack my synthetic division since I already have the coefficients underlined in red. So we'll drop the 5 down. Now be careful here if you're multiplying 5 times 2/5. So 5 times 2/5 will give us 2. Adding straight down, we have negative 20. So now you're multiplying negative 20 by 2/5. So 5 divides into negative 20, negative 4 times 2 would be negative 8. Add straight down, we have 5. 5 times 2/5, we already said was 2. And add straight down, and sure enough, we get a remainder of 0, just as we thought we would, since 2/5 is a 0. So now we look at our remaining values here, and again, those are going to be the coefficients of our quotient. So we had a cubic, degree 3, so these are going to be the coefficients of a quadratic. So 5x squared minus 20x plus 5, we'll set that equal to 0, and now we're looking for our remaining 2 zeros. Now notice there are 3 terms here and they all have a common factor of a 5. So I would start by factoring out your greatest common factor. So that will leave us with 5 times the quantity x squared minus 4x plus 1. And now we really need to find the zeros of x squared minus 4x plus 1. And sadly, that does not factor. So we'll go ahead and utilize our quadratic formula. So x is equal to the opposite of b. In this case, our b value is negative 4, plus or minus the square root of b squared. So make sure you put that negative 4 in parentheses because you want to square the whole thing, minus 4 times a times c, all divided by 2 times a. Now, if I jumped into that too quickly and you might be wondering what happened to this 5 out in front, remember, it's essentially multiplication here, so it's almost like you could think of this as I'm dividing both sides by 5, and if I divide 0 by 5, we know we're still going to end up with 0. So that 5 divides out, and that's why I'm just solving x squared minus 4x plus 1 is equal to 0. So let's simplify here. We have x is equal to positive 4 plus or minus the square root of a positive 16 minus 4 divided by 2, which will be 4 plus or minus the square root of 12 divided by 2. Then remember, when we simplify the square root of 12 is 4 times 3, and the square root of 4 is 2, so that will simplify to 2 times the square root of 3. So we have 4 plus or minus 2 times the square root of 3, all divided by 2. And then you can simplify here because 2 can divide into both the first term and the second term. So 2 divides into 4 2 times, 2 divides into 2 1 time. And so we're left with our remaining 2 zeros, 2 plus or minus the square root of 3, which is really 2 plus the square root of 3 as one answer, and 2 minus the square root of 3 as my second answer. So we have 2 remaining zeros. So going back to my list, now we have all 4. So we had negative 1 and 2/5, and these 2 are the rational zeros. Remember, they were on our list of possible rational zeros. And now we have added to this list 2 plus the square root of 3 and 2 minus the square root of 3. And notice these 2 zeros were not on our list because these are not rational zeros, but rather these are irrational zeros. You cannot write these numbers as fractions. They're decimals that never terminate and they never repeat. So the first part of the question is done. The first part said, find the zeros, and we have found all of the zeros, and there are 4 of them. Now the second part of the question asked us to write the polynomial in factored form. So the name of the polynomial was p of x, and this is where we can use our factor theorem. Because if we know the 0, for example here, the first 0, which was -1, knowing that 0 helps us build the factor. Then the factor is always x minus the 0. So in this case, that would be x minus -1. So that will simplify to be x plus 1. That's the factor that produces the 0 of -1. My next 0 is 2/5, so that produces the factor of x minus 2/5. And then we do the same thing for the remaining 2 zeros, the ones that are irrational. So 2 plus the square root of 3 produces x minus. Now be careful because 2 plus the square root of 3 has 2 terms, and we want to subtract the entire quantity, both terms. So we do need parentheses around that 2 plus the square root of 3. And then same thing with 2 minus the square root of 3. So that produces x minus 2 minus the square root of 3 as my remaining 2 factors. So I'll recopy those here. Now, the only thing left to check is to be sure that our leading coefficient matches the original. So remember, I'm calling this function p of x to match the original. But right now, you'll notice that my leading coefficient here in front is just a 1. So let's go back to the original polynomial. And if you go back, you'll notice the original polynomial had a leading coefficient of a 5. So in order for these two forms to be equivalent, I need to make sure that the leading coefficients match. So therefore, I can put a 5 here in front as my coefficient. And once I have the 5 there, then this would work as my factored form.